So this video is continuing in thermodynamics, and for this video we're going to be focusing on Gibbs free energy. So what is Gibbs free energy? If you've taken AP biology, you probably talked about Gibbs free energy. And Gibbs free energy is a measure that can tell you if a reaction is going to occur under the conditions that are present, and if you are going to get the products in this reaction. So the second law of thermodynamics helps determine whether a process is spontaneous and uses changes in Gibbs free energy to predict whether a reaction will be spontaneous in the forward, meaning making products, or the reverse direction, which means instead of making products, it's actually going to make reactants from the products. Or whether the reaction is at equilibrium. Don't worry about that yet. You're going to get to that unit, but it's going to come into play. Gibbs free energy is going to come into play for the rest of the year. So the spontaneity of a reaction involves two concepts. We have to focus on the enthalpy, the enthalpy of the reaction and the entropy. Both of those things play a role in whether the reaction will be what we call thermodynamically favored. That's what we're looking for. Is this reaction thermodynamically favored? So there's two things that determine, those are the two things that determine if it's thermodynamically favored. Well, what kind of reactions are thermodynamically favored? Well, the first thing that we can focus on is the enthalpy. If a reaction is exothermic, so giving off heat, that is a favored situation. If it is also increasing in disorder, then we will consider the reaction as thermodynamically favored, or sometimes we call it spontaneous, meaning once it gets started, it's going to keep going until you run out of reactants. So, for example, a combustion reaction. A combustion reaction is exothermic. It's getting more disorderly. Once you set something on fire, it's just going to keep burning until you run out of the reactants. That is a thermodynamically favored reaction. But we've also observed that sometimes, if a reaction is endothermic, it can also be thermodynamically favored. Even though that's not the way that makes things easy, it can be thermodynamically favored. So we have to look at both the enthalpy and the entropy to determine if a reaction is thermodynamically favored. Notice I keep saying those words, thermodynamically favored. It's really, really important that you refer to a reaction as thermodynamically favored. Is it spontaneous? Yes. But not all spontaneous reactions happen quickly. So even though a reaction can be considered spontaneous, it might be really, 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 really slow. So you have to keep in mind, for the AP exam, you need to use the words, the reaction is thermodynamically favored. So how do we know if a reaction is thermodynamically favored using Gibbs free energy? Well, we're going to look at a couple of things. Thermodynamically favored reactions are the ones that are always thermodynamically favored are exothermic and are getting more disorderly. If the situation is different, we can use the values and the signs of the enthalpy to determine if the reaction is thermodynamically favored or not. And we can use this equation. Delta G is equal to delta H minus T delta S, where T is the absolute temperature. So what if we are talking about a general reaction, meaning one that is exothermic, if delta H is a negative, and, let me erase that, and it is getting more disorderly, meaning delta S is positive, then algebraically, if you have a negative minus a positive, aren't you going to get a negative value? Because keep in mind, the temperature is in Kelvin, which means it's going to always be positive, so that's going to help us out. And what does a negative delta G mean? Hopefully you've heard that by now. Negative delta G's means that it is thermodynamically favored. And that's what we're looking for. We're looking for negative delta G's. If the situation's not like that and you end up with a positive delta G, well, then the reaction is not thermodynamically favored. So keep those two things in mind when we're talking about the reactions. A negative delta G means the reaction is thermodynamically favored. Delta G equals negative, thermodynamically favored. If you end up with a positive delta G, that means it is not thermodynamically favored, which means under those conditions, the reaction will not produce the products that you are looking for under those conditions. So the signs are really, really important. You need to know the signs of delta G's and to determine if a reaction is thermodynamically favored or not under the conditions that you are studying it. So, just real quick, negative delta G's, sometimes you see it written as delta G is less than 0. Get used to your alligators. That means the reaction is thermodynamically favored or quote-unquote spontaneous. If you have a positive delta G, or delta G is greater than 0, then this reaction isn't necessarily going to produce products. It's more likely to make reactants go in the reverse direction, if that's even possible, which means it's not thermodynamically favored under the conditions you are talking about. What if delta G is equal to 0? We've had that before. If your E of the cell is 0, meaning your battery is dead, then delta G is 0. That means your reaction is equilibrium. I know we don't know what equilibrium is yet, but that's coming, and we usually see this for phase changes. So when something is changing phases, we'll see at the phase change, G is 0, and you have reached equilibrium. So just keep that in mind. So, using the signs to determine if a reaction is thermodynamically favored. Let's look at a reaction and see what the signs are going to tell us. A lot of times they're going to just give you enough information so you can determine the signs to determine what the sign of delta G is to decide if it's thermodynamically favored. So here's a reaction, the combustion of propane. And they give us the balance equation, and then they tell us something about the enthalpy. Well, so what do we know about the enthalpy? Delta H is less than 0, which means it's negative. They're telling us that. And they're asking us if the reaction is thermodynamically favored at 25 degrees Celsius. So the second thing we need to know is what's the delta S. So let's look at the reaction. So to determine the sign of the delta S. So in this reaction, we are going from 1 mole of propane, which is a gas, to 5 moles of 5 moles of oxygen, which is also a gas, to make 3 moles of carbon dioxide and 4 moles of water, gas. So what do we have over here? We have 6 moles of gas, and then as a result, we are producing 7 moles of gas. And so based on that, what can we say about the entropy value? This reaction is getting more disorderly, which means the entropy is positive, more disorderly. And so therefore, because we know delta H is negative, delta S is positive, is this the way the universe wants to go? Does the universe want exothermic reactions? Absolutely, the universe wants exothermic reactions. Easiest way to go. Does the universe want more disorder? Yes. So we want delta S's to be positive. So is this, based on both of those concepts, doing what the universe wants? Yes. So if we were to substitute in those values, into delta G equals delta H minus T delta S, and substitute in a negative for enthalpy and a positive for entropy, mathematically that would give us a negative for delta G. And so since delta G is equal to a negative, what can we say about this reaction? It is thermodynamically favored. So let's look at another reaction and see, is this reaction thermodynamically favored? So looking at the reaction, we have sulfur dioxide plus oxygen making sulfur trioxide, and they give us some information about the enthalpy. So it says the enthalpy is less than 0, which means delta H is negative, and this is exothermic. All right, now what about delta S? Delta S, when we look at this reaction, we have gas, gas, gas. So we can't really use states. So let's look at the moles. We have 3 moles of gas going to 2 moles of gas. Is that getting more disorderly, less disorderly? That's actually getting less disorderly, which means delta S is negative, less disorder. So, is this reaction going the way that the universe would want it? Well, for the delta H, yes, exothermic. But for the delta S, it's getting less disorderly. We have a problem there. So if we were to take those values and plug them in, delta G is equal to delta H minus T delta S, and we were to plug in a negative value for the H minus the T and a negative value for the delta S, what's going to determine the sign of delta G? And in this case, the thing that's going to determine the sign of the delta G is going to be the temperature. Why? Because if this number is really low, then a negative times a negative is going to give you a positive, and so that could make this number really, this part of the equation become positive. Then that would give us a negative delta G overall. But what if this is really big? Then this value for the T delta S becomes really, really big, and that would give us a positive delta G. So sometimes whether the reaction is thermodynamically favored or not will depend on the temperature. And reactions can transition from non-spontaneous to spontaneous as the temperature increases. So a quick, easy way that I like to show about remembering this is plugging in the signs of the H's and the S's into the calculation of delta G minus equals delta H minus T delta S. And that can help tell us, is this reaction thermodynamically favored? So here's a quick, easy way to remember it, and it's the coordinate plane that you learned about in math class. So we're going to make our axes represent the delta H and delta S. So X versus Y. X comes first alphabetically, so does H. So we're going to make the x-axis delta H. And we're going to make the y-axis delta S. So in the first quadrant over here, what can we say about our delta H values? Over here, delta H values are negative. And over here, delta S values are positive. So if delta H is negative and delta S is positive, and you plug that into this equation when delta H is negative and delta S is positive, that's going to give you a negative value. So when is this reaction thermodynamically favored? Always. All right, what about down here in this quadrant? So what can we say about delta H values over here? Delta H values over here are positive. delta S values over here are negative. And when you have a positive H and a negative S, what does that do when you plug it into the equation? That gives you a positive delta S, which means when is this reaction thermodynamically favored? Never. Can you get the reaction to go? Yeah, you're just going to have to put in a lot of energy to get it to go. All right, what about the two other quadrants that are left? All right, in this quadrant, delta H's are positive, delta S's are positive, and if you plug a positive delta H and a positive delta S, what's it going to depend on? It's going to depend on the temperature. So when is this thermodynamically favored? At high temperatures. Well, what's considered a high temperature? Well, it depends on the reaction. It's relative to the reaction. What about the last quadrant? H's are negative, S's are negative. So when is this reaction thermodynamically favored? At low temperatures. At low temperatures, you're going to get a negative delta G, and as the temperature increases, it's going to transition to a positive delta G. So you can use this to help you remember the different quadrants and what does it mean. Always high, never low. All right, what about calculating Gibbs free energy? Well, you've already learned how to calculate enthalpy, and you've learned how to calculate entropy, and if you know how to do those two things, then you know how to do Gibbs free energy. If you know the values of enthalpy and entropy, then the sign and the magnitude of delta G can be calculated. But one of the things you need to be aware of are the units. Enthalpy values are in kilojoules per mole, but entropy values are in joules per mole Kelvin, and delta G is usually in kilojoules per mole. So if you're going to use the calculation, you're going to have to watch out for your units, and something is going to have to get converted. So remember, delta G is equal to delta H minus T delta S. The delta S is usually what we will change. We will usually change it to kilojoules per mole, and then you'll be able to put everything in and plug and chug. Note that the temperature must also be in Kelvin, because that's going to take care of the Kelvin in the entropy units, and then you'll be able to add the two together. So, a quick calculation example. Calculate the free energy change for the formation of nitrogen monoxide from nitrogen and oxygen at 25 degrees Celsius. So there's our balanced equation, and they're giving us two things. They are giving us the enthalpy and the entropy values. And the question is the reaction spontaneous under these conditions, or is it thermodynamically favored? Would be better wording. So a couple of things we need to do. First, change your temperature to Kelvin, to 298 Kelvin, 25. Then we're going to plug into our equation. Delta G equals delta H minus T delta S. Plug in your delta H, okay, minus the T and the delta S. Now, watch out, because we've got this one in joules and this one in kilojoules. So the first thing we're going to have to do is change one of those. Typically, we change the delta S to kilojoules. So in the next step, that's all I did right there. Change the delta S to kilojoules. And look what happens when we multiply the temperature times the delta S, then our Kelvin units are going to go away. And so we have delta G equals the value of the entropy minus T times delta S. And here, now we just have to type this into our calculator, and we end up getting positive 173 kilojoules per mole. So Is this reaction thermodynamically favored? Well, what did we get? We got a positive delta G, and that tells us, because we got a positive delta G, this is not thermodynamically favored. Why? What was the problem? Well, look what happened. We had an endothermic reaction that, according to the delta S, is getting more disorderly, but this overruled this. So let's calculate the Gibbs free energy for the following reaction. So we want to calculate delta G, and they're giving us this reaction, and they give us a table, and in the table we have enthalpy values and entropy values. So, given those values, we should be able to calculate the delta G. So what are the things that we know? We know the delta H's, and we can calculate delta H. Delta H is equal to negative 1652 kilojoules per mole. We know the delta S value, so we can calculate delta S. Delta S is equal to negative 543 joules per mole Kelvin. By the way, we already did those two calculations way back on practice problem number 2. So knowing those two things, let's calculate a delta G. Delta G is equal to negative 1652 kilojoules per mole minus temperature. What's the temperature? Well, there's a hint in here what the temperature is. They didn't actually give us a specific temperature, but they gave us the information to get the temperature. And it's in the table. If you look at your delta S values and your delta H values, you see that little naught symbol. What does that little naught symbol mean? Standard conditions. And what's the temperature at standard conditions? 25 degrees Celsius or 298 Kelvin. So here our temperature is 298 Kelvin times my delta S. Negative 543 joules per mole Kelvin. Now, we're back to that unit problem. My delta S is in joules, my delta H is in kilojoules, so I need to change that. So all I have to do is divide by 1,000, which gives me 0.543 kilojoules per mole. Kelvins go away. Plug everything into your calculator. Delta G is equal to negative 1490 kilojoules per mole. And so the question is this reaction thermodynamically favored? And the answer is yes, it's thermodynamically favored under these conditions. Why? Because delta G was negative. A couple of final notes. There's another way to calculate delta G. You will find several delta G calculations on your equation sheet. Here's another one. You can calculate delta G using the summation process. Delta G of the reaction is the sum of the delta G of the products minus the sum of the delta G of the reactants. You can do it that way, just like we've done for H and S. You could also do it through a stepwise process where you have to flip and multiply your delta G's. So we've been doing this with enthalpies and entropies, and now you might have to do it with delta G's. Works exactly the same way. The other thing to pay attention to is watch your units. They will mess up your conclusions if your units are not consistent within the calculation. So don't lose your units or don't mess up your units, watch out for delta H's being in kilojoules, delta S being in joules, delta G's being in kilojoules. Pay attention to those kinds of things. Signs are important, so make sure you can do quick calculations with just signs. Either use the coordinate plane process or just make sure you understand this table. If things are going the way the universe wants it to go, with a negative enthalpy and a positive entropy, then delta G is negative, which means it is thermodynamically favored. That's the way the universe wants it. What if we're going away the way against the universe? Positive enthalpies, negative entropies give you positive delta G's, not thermodynamically favored. All right. What if your signs are the same? If they are the same, it depends on the temperature. If they're both positive, then they are thermodynamically favored at high. If they're both negative, it's thermodynamically favored at low. Last thing about delta G's, sometimes you have to connect them to other AP topics. We've already covered electrochemistry, hopefully, so you've already hopefully done this calculation. Delta G is equal to negative nin phi. There's your E of the cell, Faraday's constant, moles of electrons. If you can plug those things in, you can decide if it is a galvanic cell or an electrolytic cell. All right. The other connection that you have is to equilibrium, which the important thing in equilibrium is the value of K. So you should be able to use this calculation. If you are given K, calculate G. If you're given G, calculate K. R is a constant. It's on your equation sheet. T is a temperature. And Ln is natural log. Sometimes we get messed up when we're going from K to G. So just know, and if you need help with this, you can go to a math teacher. But K is equal to the inverse natural log, which is E, raised to the delta G divided by negative RT. I just did algebra to rearrange this equation to get it to solve for K. So E is inverse natural log. All of those, this part of it at the top, is going to become an exponent of E. And all you have to do is plug in your delta G, your R, and your T. Watch out here because R's units are in joules, which means your delta G needs to be in joules. And here's the last thing that you will have on that, which once you get through equilibrium, this will make more sense. But if your delta G is a negative, then your K is greater than 1, which means that reaction proceeds towards the products. If your delta G is positive, then that means your K is less than 1, and that means the reaction proceeds towards the reactants to get to equilibrium. If your delta G is 0, then your K is equal to 1, which means you are at equilibrium, and this is again a phase change or a dead battery.